Let me share my screen first. Then I will show you the problems that will be we will dealing with with the direct stiffness method. So this is your 12th week and the final week for the structure analysis course, wherein we have started with the analysis of the determinate structure, and then we have moved to the moving load diagrams, that is influence line diagram, and then we have analyzed various no, indeterminate structures and try to find out the various reactions, movements, and deflections that are there in both determinate and indeterminate structures. So now this is your final week, and my name is Pranav Mahajan. I am the TA for this course. I am a PMRF scholar in Structure Engineering Division, Department of Civil Engineering from IIT Madras. So till now, what you have covered. So up to week 11, we started with the analysis of statically determinate structures. So what we have seen in that, in first week we started with the basic foundation of this course, that how we can calculate the reaction and moments at various support ends, and what kind of reactions are developed that when it is a fixed end. So how many reactions are developed in that, whether a vertical reaction developed, horizontal reaction developed, or moment is also rotation restriction is also there, that is also being seen, that how it changes from support to support. So in that we have seen that in roller support we have one vertical restraint, whereas in hinge support we have two restraint in horizontal as well as in vertical direction, whereas in fixed support we have three restraint, that is horizontal restraint, vertical restraint, as well as the movement rotation restraint is also there. Then we proceed further in the analysis of the beam. So analysis of beam, we have started with the equilibrium equations. So what we have seen in that, we have seen that how the shear force and bending moment changes along the length of the beam, and what kind of maximum value is observed in the whole beam, that will be helpful in determining the values of maximum stress that are developed in a particular section, and that would be helpful for us in designing the particular beam or frame or a truss. In week 2, we have moved for the analysis of a plane or space truss. So for the planar truss, we consider the truss to be a two force member in which the compression and the tension force is acting, and there is no bending moment along the length of the beam. So to analyze the and determine the forces that are there in the beam, we have utilized two methods. One is the method of joint and another is the method of sections. So in method of joints, we have applied the equilibrium equations and determined the value of uh, forces that are developed along the different parts of the truss members, and determine the whether that member is a compression member or a tension member. And whenever the complexity is very large, we utilize the method of section, in which we cut the whole truss into the two parts and determine the value of unknown force that is there in the truss member using equilibrium equation, and most probably we use the summation of moment about any point equal to zero. Based upon that, all other the known reactions will be equal to zero. Only the concerned force that is there in your particular problem, that can be determined using that summation of moment equal to zero. After that, we have utilized the concept that how we can determine the deflection in the truss member. So in that, we have utilized the concept of principle of unit load method, which also takes into account the method of virtual work, which says that the internal work done should be equal to the external work done. So in this case, what we will do, we will apply a unit load in the direction where the deflection is about to to be calculated. So when we apply that force in that particular direction, so based upon the um, um, method of virtual work, which says that internal work should be equal to the external work, we have come into the into a equation that is N L upon AE, where capital N is the force is the force due to the externally applied load, and then small n is the force due to the unit force applied in the direction where the horizontal deflection is required to, or horizontal or the vertical deflection is required to be calculated. And based upon that, we can calculate the deflection about that particular joint, whether it is there in horizontal direction or it is there in vertical direction. From truss, we have moved to the beams and frames, in which to determine the deflections in beams and frames, we utilize the concept of moment area method, conjugate beam method, and virtual work method. All these three methods help us to determine the deflections and slopes that are there in statically determinate structures. So, completing the concept of statically determinate structure, we have moved to the portion wherein we are required to calculate the reaction due to the moving loads that is there. Example, when a train is moving over a bridge, how much reaction or shear is developed at particular section, that is required to be calculated in order to determine the stresses that are there due to the moving loads. So influence line diagram help us to determine the value of reactions at the support, as well as the shear and the and the bending moment at any particular section due to the moving load along the length of the beam. So in that case, we are utilizing the concept of Mueller-Breslau principle and determining the maximum bending moment and reaction that are developed in the whole length of the beam. After that, we have moved to the analysis of statically indeterminate structure. So from week 7 to week 11, we have covered the analysis of the statically indeterminate structure, wherein we started with the force and the stiffness method, and we introduced various concepts and methods that are there for force method as well as the stiffness method. We have also seen that how we can utilize the concept of method of consistent deformation in trusses. So in that case, what we have done, we have taken a truss and we have determined the degree of static indeterminacy. And based upon the degree of static indeterminacy, we remove the redundant and make the structure to be determinate. So after making the structure to be determinate, we analyze the structure and we again made the structure redundant and check how the forces is there in the member, and then based uh, upon the values that we have derived, we can determine, we have made the truss now to be determinate, and then we are solving the problems as a determinate structure. In week 9, we have moved to the continuous beam. In continuous beam, how we solve the problems? We have solved the problems using three moment theorem. So in three moment theorem, we have derived an expression to determine the end moments in the continuous beams, and using unit load method, we have come up to a certain equation which will also incorporate the concept of settlement of support. So how you can determine the end moments in the large continuous beam, which are also indeterminate, that we have seen in the week 9. Then later on, we have moved to the slope deflection method, wherein we have seen that how end moments are calculated using slope deflection equations. And on week 11th, that is the previous week, in what we have seen that how moment distribution method is utilized to determine the end moment in a structure. So in this, we have taken into the account the concept of distribution factor as well as the carryover moment in order to determine the end moments at various point along the span of the beam as well as for the frames. Now, incorporating all this method, now we are moving to the direct introduction to direct stiffness method. So this method is mostly will act as a linkage between the end of this course and the advanced course is related to the structure analysis. So till now you have solved the problems related to one isolated beam, one isolated frame span. So what will happen when you will be having large spans and large beams that are there in a building or suppose in a bay frame? So then how you will calculate? So in that case, you can't be able to calculate at each and every point using manual calculation. So this method will help you to make a certain code that will help you to determine the values of forces that will be developed using this method. So what direct stiffness method says that suppose you have a beam. So suppose you have a continuous beam. In this, how the deflection profile look like? So its deflection profile will look like this. So this is how the deflection profile of the beam will look like when it is subjected to different loadings. Okay, so in this case, your forces will be developed. So let the forces will be F1. Here it is F2. Here it is F3, and here it is F4. So how you will be solving these values? So in that case, we already know that stiffness is equal to force per unit displacement. Okay, so this means your force will be equal to stiffness into displacement or deformation. Let me write it as deformation. So let the deformation here will be D1, D2, D3, and D4 in the member. So then how you will write the matrix? So that will be F1, F2, F3, F4. And here your stiffness matrix will be K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, and similarly for the fourth row also, you can write it like that. So in this case, when you multiply it by deformation, you will get to know the value of the forces. Here, this stiffness matrix, so K is stiffness matrix. It is symmetric. Okay, that means your K12 will be equal to K21, K13 will be equal to K31 and so on. So how you will solve the problems related to this? So at any particular joint, so let's start with a truss member. So when you have a truss, subjected to a point load at the top, so in this case, your axial deformation will be in this coordinate. So this is your local coordinate. But in journal, you observe the deflection in XY coordinate or in horizontal and vertical coordinate. So this is your global coordinate. So how you can transform the values from the global coordinate to the local coordinates? So that you will do using transformation matrix. So what is the main purpose for this is that so matrix method helps you to divide a whole lot complex problem into smaller problem and then you can assemble them. So this method helps in dividing a complex problem into smaller parts which you can solve and then assemble them. Okay. So in case of truss, so if you divide the whole member into three parts, so let's start first with the stresses. So your stress will be E into strain, that is Young modulus into strain. Now your F upon A, you can write it as stress, but in this some more components will also be there due to the Poisson effect, and then E into U by L, where U is the deformation. So now how you can write this U? So U can be written as L upon AE into F. So what this is telling you? So this is telling you that F is equal to AE upon L into U. So now this AE upon L for the truss member or when any member is subjected to axial forces, that will be the stiffness value. Okay. So now let's move to the this problem. So in truss problem, if you divide it into three parts, so let's I am suppose taking the left part of the problem. So in that, what you will do, you will make one end fixed and one end free and apply the loading. So if you apply the load along the axis of the member, so in this case your P will be P1 dash. So due to P1 dash, a reaction will be developed that will be P2 dash, and this will be along your local coordinate. So in this case, your P1 dash will be equal to AE upon L into U1 dash, and your P2 dash will be equal to minus AE upon L into U1 dash, because this P2 is derived from the force that is acting in the direction in the direction of the applied load. So P2 is your reaction component, which is in opposite to the direction of the applied force, and that's why minus sign came into picture. Whereas when you are applying force from the other end of the member, so you will fix the other side of the member to be fixed, and now you will apply force in this direction. So suppose due to this your u2 your deformation in the member will be u2. So now in this case your p2 double dash, because in that case is p2 dash, will be equal to ae upon l into u2, and your p1 double dash will be equal to ae upon l into u1 dash. Okay, so if you add up all the values, so what you will get, so your q1, will be equal to p1 dash, so this will be minus 1. Okay, so your q, that is the force that will be developed in the member, will be equal to p1 dash plus p1 double dash, and that would be equal to ae upon l u1 dash minus ae upon l into u2 dash. Similarly, your q2, that is a force in the other joint of the member, will be equal to ae upon l into u2 dash minus ae upon l into u1 dash. So now writing in matrix form, this q1 and q2 will be equal to 1 minus 1 minus 1 1 into u1 dash u2 dash into AU over L. Okay, so this let me write AU over L in the front, then it will be okay. So here this portion AE over L 1 minus 1 minus 1 1, this is your local member stiffness matrix. Okay, so now how you can write this local member into this global stiffness? So for that you are need to use the deformation matrix. So how we will do? Let's see further. So let's see, you have a member like this. In this portion, you are having the deformation as u1 dash. In this portion, you are having the deformation as u2 dash. Okay, so this is your joint A, joint 2, joint 1 and joint 2. And here you are defining the local coordinate system as this is y dash and this is x1 dash. Okay, But in case of global coordinates, your deformations will be like this. That would be u2, this would be v2, and this will be u1, v1, and let this angle be theta. So then how you can relate u1 dash with u1 and v1? So how we can write? We can write it like this. So we can write u1 dash is equal to u1 cos theta plus v1 sin theta. Okay. Similarly, you can write u2 also as u2 cos theta plus v2 sin theta. So in matrix form, how you can write this? So this is your local deformations, and one matrix will be there in between. That would be your transformation matrix. And in global matrix, what is it is there? It is u1 v1, u2 v2. So how you can write the above equations in matrix form? So in that case, this will be cos theta, sin theta, and this will be 0 0. Now for u2, this will be 0 0, and this will be cos theta and sin theta. Okay. So this is your transformation matrix uh, from conversion from global stiffness matrix to local stiffness matrix. In other words, you can also write the same using the inverse of the transformation matrix, and then you can write the uh, global stiffness matrix in terms of the local stiffness matrices. So that means you can write u2, u1, u2 as, so let me give some notation as lambda x, lambda y. Okay. So this is for the deformations. Now we'll see how you can write this when you have to write in terms of the global stiffness matrix. So this is your local stiffness. Sorry, this is your local deformation, and this is your global deformation. If you need to write in reverse sense, then how you will write? So in that case, let's suppose you have a member. In this, the local forces are q1 dash, q2 dash, and in this case, you are having the global forces to be in this coordinate system. So let these forces be P1, P2, and here it would be P3 and P4. Okay. So how you will write these forces? You can take the inverse of the previous matrix also. Then you will be able to write this. So this will be P1, P2, P3, P4, and that will be equal to cos theta, sin theta, cos theta, sin theta. Okay. This is how you can write for the global stiffness, global matrix in terms of the local matrix. But we also know Q1 and Q2, as we previous derived, it will also depend upon Ke, which is the local stiffness matrix, multiplied by U1, U2, U1, U2 dash, okay, which are the local deformations that are there in the matrix. So substituting the value for Q1 and Q2 in previous equation, what you will get? You will get P1, P2, P3, P4 equal to this matrix transpose, that is the first matrix, multiply by the Ke, which is the element matrix that we have uh, taken for the stiffness, multiply with the transformation matrix T, and then multiply it by the U1, U2, U3, U4, U1, V1, U2, V2. Now, this matrix that we derive from the local stiffness matrix, that would be your global stiffness matrix. Okay. So first of all, you will calculate the local stiffness matrix in this form. So this is your first the local stiffness matrix. Okay. Then afterwards, you derive the equation for the deformations in global stiffness matrix, and then you can write them in global stiffness matrix, and then substitute the value of U1, U2, U3, U4, and then you can get the value of P1, P2, P3, P4, which are the forces in the global stiffness matrix. Okay. So in this case, your K, which is your global stiffness matrix, will be equal to, so this will be equal to lambda h square, lambda x, lambda y, lambda x, lambda y, and this will be lambda y square. Here it comes minus lambda x square minus lambda x lambda y, and this would be equal to minus lambda x lambda y and minus lambda y square. Here minus terms will come. So this is your global stiffness matrix. So this is for the case when you have the axial deformation in the member. So what will happen in case of the beam bending? So in that case, we will see then how we can solve the problems. So in case of beam bending, so let's suppose you're having a fixed beam in which you are defining the vertical deformations as u1 dash and u3 dash, and the rotations we are defining it as u2 dash, and here it would be u4 dash. Let the coordinate system will be like this. So this is your x dash and this is your y dash. Okay. And assume there is no axial deformation. Okay. So in this case, what how you can derive the stiffness matrix? So let's suppose you have a beam like this, like you have already constructed. In this, if you provide unit displacement to u1, so how the beam will deform? So beam will deform like this. So if you are providing unit displacement, and then the moment that will be generated due to this will be like this and like this. So this will be 6 EI upon L square. This will also be equal to 6 EI upon L square. And here the vertical deflections reactions will be 12 EI upon L cube and 12 EI upon L cube. Okay. So how we define the stiffness also? So in this case, since you are providing the vertical displacement, so the vertical direction reaction would be K11, and due to the application of vertical displacement, rotation in the joint 1 will be written as K12. Then third, for the joint 2, it will be written as K K13, and this will be written as K14. Okay. So similarly, if you have the rotations provided in the no joint and 1 and 2, suppose this is your node 1 and this is your node 2. So if you apply rotation only, so this is unit rotation that is provided to the member. So when the unit rotation is provided, then the beam no longer have zero slope at the end where the rotation is provided, whereas the other end will have zero rotation. So in this case, your moment that will be developed will be 4 EI by L, and in other case you will get it as 2 EI by L, and the reactions that will be developed, that will be equal to 6 EI upon L square, and in other point it will be 6 EI upon L square. So in this case, this would be due to rotation, this would be your K22. So this is joint 1, so this will be K21. This would be your K24, and this will be your K23. Okay. Similarly, if you move the joint 2 first, if you take U3 in the positive y direction, if you provide displacement in that, and then if you provide the rotation, so the final stiffness matrix that will be developed for a particular member, so that would be equal to like this. So that will be equal to 12 EI upon L cube, and then it will be 6 EI upon L square, and then 12 EI upon L cube, and again it would be 6 EI upon L square. For no join 2, what you have received, it is 6 EI upon L square, 4 EI upon L, then it is minus 6 EI upon L square, and then it is 2 EI upon L. And similarly, if you move the joint, your node 2 in vertical direction, if you provide unit displacement to that, you will receive the value as negative to the one that you have obtained in the first case. Whereas due to rotations, you will receive the value as 6 EI upon L square, and this will be 2 EI upon L, and this will be same minus 6 EI upon L square, and this will be 4 EI upon L. Okay. So this is your final stiffness matrix in case of the bending, and when the axial deformation is also allowed. So if axial deformation is allowed, then what will happen? So in that case, let's again draw the beam. In this case, U1 will also come into picture. So this is your U1. This will be your U2. So let me write it as U1, U2 dash. This will be your U3 dash, and here it would be, so this would be your U4 dash, U5 dash, and this will be your U6 dash. Okay. So you can, what you can do, you can decouple them and write it into two parts. So you can solve for the beam bending separately, like the previous thing we have already seen for beam bending. So that would be, this is your U2, U3, and this would be your U5, U6 dash. Okay. Plus, now take the beam for the axial deformations. So for the case of axial deformations, here these are the axial deformation, that is U1 and U4. So you can write them as separately. that here it is your 4 by 4 matrix that we have written previously. And here what we have written as, we have written it as AE upon L into minus 1 minus 1 minus 1 1 2 by 2 matrix, and combined you have 6 by 6 matrix. Okay, so you can decouple them and solve them separately and get to know the values, and then you can get the whole stiffness matrix for the frame structures. So let's solve a simple problem related to a truss. So suppose you have a truss like this, okay. So for this case, we have already solved using simple methods. So how you have received the values? So for that you got the values as, in this case, this part will be in compression and this part will be in tension. So here the values you have received is P by root 3, and here it is P by 2 root 3. Okay, so these are the answers you already know. Now how to solve using the stiffness method, then now we will see. For this case, you take the triangle and you mark the coordinate as for the whole, for each joint. Okay, so for let me write, this would be node 1, this would be your node 2, and this would be your node 3. The numbering of the nodes will also depend upon the end condition that is provided to you, because at the end when you are required to assemble the whole problem, so that would be not be so much complicated for you, and by solving the problem you will get to know that how you can number the truss or a beam element, and how much amount of complication that will be observing when you will change the numbering system, and how much it will be get easier if you make the node 1 to be the one which is will be having no supports, because other supports will get 0 and the only part that will be remaining will be only the node 1. So here it would be node 1 2 3 4. So this is 1 2. So for node 2 it would be 3 4. For node 3 it would be 5 6. So now divide each member separately. So this 1 2, this is 5 6. So here the value of the coordinates will be 0 0, and here it would be L by 2 into root 3 L by 2. Okay. Similarly, for other member, you can write it as So now this is your 4, this is 3, this is 5, this is 6. So here the coordinates would be 0, 0. Here would be L0. Here it would be L0. Here it would be L by 2, 3 by 2, root 3 by 2 into L. And the stiffness here, so let K1 will be the element stiffness. This will be K2. This will be K3. Okay. So these are your elemental stiffness. So in this, how members are connected to each other. So member one. So this is your members. This is your ith node. This is your jth node, and this will give you lambda h lambda y. So for member one, it is connecting from 3 to 1. So that means this is your member one. Your member two is from 2 to 1. So this is your member two, and then this is would be your member three. So your member three is from 3 to 2. Why the numbering is important? Because from I to j, the value of lambdas you are required to be calculated. In what direction the theta you are considering, that matters a lot. Okay, so in this case, you are getting the value of lambda as 1 by 2, root 3 by 2, and then minus 1 by 2, root 3 by 2, 1, and 0. Okay, so how you will derive the um, matrix, that is the that is the global matrix for for member one. So we will write it now. So your K1, we have written it as lambda square. So it will come as 1 by 4 lambda h lambda y. It would be root 3 by 4. Here again it will come, and here it will come as 3 by 4. Now in this side it would be minus. Again it is minus, and here it would be plus. Okay, so this is your K1. So similarly, K2 and K3 are determined. Okay, and now the best part comes is your assembly of this matrix. So in this case, this is your 5 sets, and then it is 1 2. Okay, this is also numbering as 5 6 1 2. Now I will write the numbering, and then it will be easy for you to solve for other cases. So your K2 will be, so if there is a matrix, so for K2 it would be 5 6 3 4, and here also it would be 5 6 3 4. Similarly for K3, it would be, oh sorry, I have written this for K3. So this is 5 6 3 4, 5 6 3 4. For K2, it would be 3 4 1 2 and 3 4 1 2. Now, if you have to assemble all the three matrices, it depends upon the numbering you are doing. So your K matrix will then finally become a 6 by 6 matrix like this. So its final value will be 1 by 2, 0, minus 1 by 4, root 3 by 4, minus 1 by 4, minus root 3 by 4, 0, 3 by 2. So all these values are coming after assembling at each and every node that we have determined. So now for each and the every node, you have to see what value you will get there, and based upon that value only, you need to insert at that particular location. So this is your final stiffness matrix that will be developed for this whole truss. So, but now in this case, your D4, D5, and D6, all of them are equal to 0. So only the points that will be remaining, that will be equal to D1, D2, and D3. That means this matrix. Rest whole matrix will be equal to 0. Okay. So writing it further. So here 1 by 2, 0, minus 1 by 4, 0, 3 by 2, root 3 by 4, minus 1 by 4, root 3 by 4, 5 by 4, into D1, D2, D3. That are the deformation that will be there. And in that case, you will be having 0. That's external force. Here it is minus P and here it is 0. Okay. Solving these equations, you will get D1 equal to 0.1433 PL upon AE. Your D2 will be equal to minus 0.750 PL upon AE. And your D3 will be equal to 0.2887 PL upon AE. Okay. So now if you are required to calculate the member forces, then how you will calculate? So if member forces are required to calculate, you will calculate like this. So your member forces will be like your N1 is equal to AE upon L minus lambda x minus lambda y lambda x lambda y into the forces deformation that are there in the member. So in that member one, it is D5, D6, and then it is D1, D2. Okay. Similarly, so if you solve this, you will get the value as, so here your D5 and D6 will be equal to 0. And what values are remaining? You will get AE upon L minus 1 by 2 minus root 3 by 2, 1 by 2, root 3 by 2 into 0.411433, and here it is minus 0.750 into PL upon AE. So by this, what you will get? You will get the value of N1 as, so your N1 will be equal to minus 0.5774 P, and that will be equal to minus P upon root 3. Similarly, if you do for N2, so you will get N2 as minus P upon root 3, and N3, it will be equal to P upon 2 root 3. And all these values are same as derived earlier. Okay. So these values that you have obtained by this method is same as that you have derived by the methods you have studied in previous classes. Okay. Similarly, you can solve the problems related to beams also. In beams, not only the axial deformations, but the bending will also come into picture. Then how you will solve that problems, we will see further. So let's solve one or two problems that will clear your concepts. So in this case, you are provided with a cantilever beam subjected to combination of forces. One is the unit load, one is the concentrated load that is provided at one B end, and another is the moment. Then how you will solve? So in this case, you are required to provide with the flexibility matrix. So your flexibility matrix, that is F, would be K inverse. So your inverse of the stiffness matrix will give you the flexibility matrix. Okay. So let's isolate the problem into two. So for this beam subjected to a point load P, so its deformation will be like this. So in this case, this will be its delta, and this will be its slope. So here the value of delta is PL cube upon 3EI. So these values we have already calculated, and theta will be equal to PL square upon 2EI. Okay. So for unit deformation or for unit load, P is equal to 1. So your F11 will then become, so F is equal to P upon delta. Okay. So it will become L cube upon, sorry, this is stiffness upon delta. So this is K. Let me write it. So this is your K. So your stiffness is equal to force upon displacement, and then your flexibility will become displacement upon load. Okay. So in that way, your F11 will become L cube upon 3EI. Your F12 will become L square upon 2EI. So in this case, your L is given to be 3 meter. So by substituting that, you will get the value of F11 as 9 upon EI and F12 as 4.5 upon EI. For the moment that is provided for that thing, again your beam will shift like this, and this will be your delta, and this will be your theta. So your delta here would be equal to ml square upon 2ei, and theta would be equal to ml upon ei. Now if m is equal to 1 ln 2, your f22 will become L upon ei, and your f21 will become L square upon 2ei. So that means this value will be equal to 3 upon ei, and this value will become 4.5 upon ei. So your complete flexibility matrix will be equal to f11, f12, f21, f22. If you take ei as outside, you will get the value as 9, 4.5, 4.5, and 3. So this will be your flexibility matrix for the problem that is provided to you. Okay. So now next question. So next question incorporates all the concepts that you have seen till now for the beam beam bending. Okay. So this is the combined problem for all the concepts that you have seen till now. So let's read first. So the question says that consider a uniform two-span beam ABC, okay, which is fully fits at support A and support C, okay, and simply supported at B as shown in the figure. Okay. Now a UDL of 24 kilonewton is applied to the span AB, and a central point load of 24 kilonewton is applied to the span BC. Now we have to assume the members to be axially rigid. Okay. Now we have to determine the structural stiffness matrix, okay, and their applied load vector, then their corresponding structural displacements. After that, we can determine and member end forces and their support reactions. And finally, we have to sketch their shear force and bending moment diagrams and deflected shear. So this is the whole problem that we are required to be solved. So let's start the problem. So for this, let K11 will be there at the center of the span where the simply supported is provided. Okay. So if you provide unit rotation there, how the beam will deflect? It will deflect like this. Okay. So if the beam will deflect like this, so your this moment will correspond to K11. Okay. So if this is K11, so how you will write? So if you make it like this, Here you will get two reactions. Okay. Moments will also be developed at these points, and due to that, far end moments will also be developed like this. So your K11 finally be equal to 4EI upon L for AB section. Let me write it as A, B, C, A, B, C for AB section plus 4EI upon L for the BC section. Okay, so that would be equal to 4EI upon 6 plus 4EI upon 6. That would be equal to 1.34 EI. Okay, if you are writing the inverse of the stiffness, so your K inverse would be equal to 1 upon 1.34 EI. So now for the calculation of structure load by vector, so your structure load vector, you need to determine the n of its end forces that are there in the member. So let's divide the whole beam into fixed beam. So first, due to the simply supported load that is provided over the AB length, okay. So in this case, your FPF fixed end force that will be developed, it will be equal to minus 24 into 6 square divided by 12. It would be equal to minus 72 kilonewton meter. Your FEF 3 will be same as FEF 1 but in opposite direction. And now the reaction forces, that is FEF 2, that would be equal to 24 into 6 divided by 2. It would also be equal to 72 kilonewton. And your FEF 4 would also be equal to 72 kilonewton. Okay. So, so your this is your structure load vector. So now your equivalent nodal loads will be equal to the reverse of that you have obtained for the structure load vector. So that would be equal to like this. So here it would be 72 kilonewton. Here moment is anti-clockwise, so here it will be clockwise. And here it will become anti-clockwise. So this is for member AB. Now for member BC, again, due to point load, your FEF1 will be equal to PL square upon 8, PL by 8, sorry. So minus 24 into 6 divided by 8. So this value is minus 18 kilonewton meter. Your FEF 3 will be 18 kilonewton meter. And FEF2, due to the reaction force, it would be equal to PL by 4, P by 2, and that would be equal to 24 upon 2, 12 kilonewton, and your FEF4 would also be equal to 12 kilonewton. So now again, drawing the equivalent node for this, it would be like this. So this is your equivalent nodal load for member BC. So combining the whole beam, how it will look like. So here the force will be 72 kilonewton. Uh, and here also it is 72 kilonewton. Then we have rotations also as 72 kilonewton meter. And for BC, it is 12 kilonewton. 12 kilonewton, and the rotations that are observed are 18 kilonewton meter. Okay. So your applied load in direction of delta 1 at joint B will be equal to minus 72 plus 18, that would be equal to minus 54 kilonewton meter. Okay. So your structure load vector P will be equal to minus 54. Okay. So your structural displacements, how you can define it? So displacement will be equal to K inverse P, and for first case you have already derived it as 1.34 EI into minus 54. So by this you will get delta 1 equal to minus 40.3 EI. So since it is in negative, so that means it is in anti-clockwise direction. Okay. So how you are determining the element stiffnesses, that now we will see. So element stiffness matrix. So let how we will define the forces here. So your rotations will be F1 and F3 in clockwise directions, and your F2 and F4 are the shear force in upward directions. So by this, how you will obtain the stiffness matrix. So your stiffness matrix will be like this: 4EI upon L minus 6EI upon L square, 2EI upon L, 6EI upon L square. Your assumed directions will define that how your stiffness matrix will look like. So this stiffness matrix differs from what we have written in previous case. That is because in previous case we have taken F1 as shear and F2 as rotation, and then their directions are also different from what we have taken in this case. So that's why the position of values as well as the signs might be different from what we have written in previous case. So this is your element stiffness matrix. Okay. So for AB, so your AB, how it will look like. So substituting the values, so your KAB is becoming 0.67. You substitute the value of L along in this stiffness matrix that is provided to you, and then you will be able to determine the value of KAB. 0.34, 0.17 minus 0.17, 0.06. So this is the stiffness matrix for element AB that we have observed. And here the displacement vector will look like, so your delta 1, delta 2, delta 3, delta 4 is your displacement vector. And in this case, only first displacement that we have observed uh, would be delta 3, because from the fifth end there would be no displacements, and your displacement will be displacement 3, and that would be equal to minus 40.3 upon EI into 0, and force will be 0 due to the vertical support that is provided at that end. So hinge support is provided, so only the rotation that is minus 40.3 will come into picture, and delta 4 will become equal to 0. So due to the applied load also, the fifth end moments will come into picture. So FEF1 in this case, FEF1, FEF2, FEF3, and FEF4 will be equal to how we have calculated minus 72, 72, 72, and this would be also be 72. Okay. So your total force F total will be equal to KAB delta plus FEF. Okay, so if we write it here, so solving all the values, so you will point with 7. I think I should copy. It will be easier for me. So I will copy this again, and I will paste it here. Okay, so this is my KAB into delta. So now delta. This is delta. Okay. Now this KAB delta plus we have its and factors also. So fits and factors also we will copy. So this is our fits and factors, and I will paste it here. Okay. So this is your final equations. Okay. So from this, how you will get F1, F2, F3, F4? Now we will write. So your F1 will be equal to your third value of this matrix minus 0.34 into 40.3 minus 72. What you will get? You will get it as minus 85.70 kilonewton meter. Your F2 will be 0.17 into minus 40 point, sorry, it is minus and minus, so it will be positive 40.3 plus 72. You will get the value as 78.85 kilonewton meter. Your F3 is equal to minus 0.67 into 40.3 plus 72. It becoming equal to 45.0 kilonewton meter, and your F4 is minus 0.17 into 40.3 plus 72, and it is coming out to be 65.15 kilonewton. Okay, this will be anti-clockwise, this will be upwards, this will be clockwise, and this will also be upwards. Okay, so this is how we have solved for the element AB. So for element BC, so your KB is same as KBC because the length of the member is same. So there would be no change in fact this thing. So so this would be your KBC. Okay, and your displacement vector will now become delta 1, delta 2, delta 3, delta 4. It will become now your delta 1 will be minus 40.3 EI, others will be 0. Okay, because other end is also fixed. Now talking about fits and factors, here it is point load. So due to point load, we have calculated the values of fits and factors. And it is coming out to be minus 18, 12, 12, sorry, 18 and 12. Okay. Again, F total will be equal to KBC into delta plus FEF. And by that, you will get the values. I am writing directly the F1, F2, F3, F4 values. Okay. So that is coming out to be minus 45.0 kilonewton meter. Your F2 is 18.85 kilonewton meter. Your F3 is 4.30. Sorry, this is kilonewton meter. And your F4 will come out to be 5.15 kilonewton. Okay. So their direction will be like this. And finally, your end reactions that you will observe. Okay. That would be for support A, your VA will be equal to F2 for AB. Okay. And that value we have got it as 78.85 kilonewton. Now your VB will be your F1 for AB, and that is equal to minus 85.70 kilonewton meter. Sorry, this is MA. So MA. For support B, so VB will be sum of F4 of AB plus F2 of BC. So that will be equal to 65.15 plus 18.85, and it will be equal to 84.0 kilonewton. And your MB will be equal to F3 of AB, and it will be same as F1 of BC equal to 45 kilonewton meter. Now for support C, your VC will be equal to F4 of BC, and that will be equal to 5.15 kilonewton, and your MC will be equal to F3 of BC, and it will be equal to 4.30 kilonewton meter. Okay, this is how we have calculated the reactions for all the problems. Now let's draw the shear force, bending moment, and deflection diagram. For that, I will copy the beam from here. So this is our original beam. So let's draw a few lines. So we start with the shear force diagram. So for this, we have got the values as 78.85 kilonewton meter, and other value we will get as 65.15, and because uh, total is 84 kilonewton meter. Okay, so for the UDL, the shape of shear force diagram is linear, so it would be like this. Then it will move up for certain part, and then it will continue further like this. Okay, so here the values are 78.85. Here the value is 65.15. Maximum value is 18.85. Then the value become 5.15. Okay, so this is your shear force diagram. Now about bending moment diagram, it would be so first we will draw the end moment values. So it is 85. Then we have 45. Then we have at support is 4.3. So it is moving like this, touching the points like this, like this. Okay. So how the bending moment variation occurs? So bending moment variation occurs will be parabolic. So it will move like this. Let me again draw it. It would be like this, and then it would be linear. Okay. So this is your bending moment diagram. And what are the values you have obtained? So the values here are 85.7. Here it is 44.0 kilonewton meter. Here you have 45. Here you have got 11.35 and then 4.30 kilonewton meter. So this is your bending moment diagram. Now finally, we are here for the deflected shape. So how your deflected shape look like? So your deflected shape will move like this. Here slope will be 0. Then your slope will increase and become 0 at the support. And again, it will change at this point and reaches at point 0. Okay. So let's mark them. So this is your point A, this is your point B, and this is point C. And this is your deflected shape. So everything we have now determined for this whole beam using direct stiffness method. So this is how we solve the problems. So you can also solve the problem for frames, truss, using the direct stiffness method. So what we have covered this week. So this week we started with introduction to direct stiffness method. Then we have started to determine that how the truss problem can be solved using the direct stiffness method. Then we have determined the stiffness matrix for the bending problem that can be utilized for beams as well as for frames. Then we have solved the problem related to truss and checked that whether the values we have obtained for the member forces are same as what we have derived using the previous methods we have taken. Might be it could be method of joint or method of sections. Then we have solved one question related to flexibility matrix, and one bit question we have solved related to uh, determining the structural stiffness matrix, then applied load vector, and then fits end factors for each member. Then we have determined the structural displacement as well as the member and force and their support reactions, and finally their shear force as well as the bending moment diagram. So for this, we started with K11 calculation. So by that, we will came to know how much will be the deflection in the member, because if we multiply this K inverse with P, we will get to know the value of delta. So based upon that, we have calculated the value of fits and factors for both the members, and then we have first determine the element stiffness, and then for each member for AB, we determine the element stiffness, and then we have determined the load vector, displacement vector, and fits and factor vector. And after that, total force will be equal to the stiffness into the displacement plus the fits and factors that we have calculated. So based upon that, F1, F2, F3, F4 that we have proposed or have not calculated for both the member AB and BC. And finally, reactions and moments at support A, B, and C are determined. And after determining the values, we have plotted them and determined the shear force, bending moment, and the deflection shape diagram. So by this, your course for the structure analysis concludes, and it marks the end of your structure analysis one course. But there are other courses also for structure analysis too that will help you to solve the more advanced problem related to structure analysis. So by this, we have covered all the 12 weeks for this course. Maybe there might be one extra session wherein we will be whole summarizing the what we have covered till this week 1 to week 12, and it will be helpful for you for the exam for the registered candidates who will be giving the exam for this NPTEL course, and it would be helpful for them to have an overview of the whole course that you have covered till so far. So I hope you would have liked this course, and it may help you in your civil engineering career further, and you might become good designer and analyst of the forces and the structures. You might become a good civil engineer, structure engineer in the coming career. And by this, I end this session. Hope you would have liked this session. If you have any problem, you can contact us anytime in the in the discussion forum that is available in the Swayam app, in which the TAs will try to respond to your queries as early as possible. So enjoy your weekend. Have a nice day. Thank you.